Hello my friends and welcome back to the You Can Do TV channel. The assembly process begins with the receipt and inspection of parts, ensuring that all components meet strict dimensional controls. Automated transport systems and rotating stations are used in the assembly line, optimizing the flow of components through various workstations. Each station is equipped to perform specific tasks, ensuring precision at every stage. The lubrication circuit is thoroughly cleaned to ensure proper functioning before engine assembly progresses further. Liebherr Components Colmar SAS, located in Colmar, France, specializes in the development, assembly, and testing of high-power diesel engines, capable of reaching up to 4,500 kilowatts. These engines serve a variety of industries, including mining, energy generation, oil, gas, and rail transportation. Once assembled, the engines undergo rigorous testing on dedicated test benches to simulate operational conditions and verify performance. Finally, the engines are painted to provide protection and enhance their durability in demanding environments. This detailed process ensures that Liebherr's high-power diesel engines meet the highest standards of quality and reliability. Heat treatment, such as induction hardening, is applied to enhance surface strength and wear resistance. Processes like shot peening are also used to improve fatigue resistance. After forging, pre-machining is performed using CNC turning and milling machines with integrated process measurement to achieve the desired dimensions. The crankshaft undergoes rough machining to remove excess material and prepare it for subsequent precision processes. Specialized machinery ensures precise machining, achieving tolerances in the thousandth of a millimeter. Once heat treatment is completed, the crankshaft undergoes finishing operations, which include grinding to achieve exact tolerances in the micrometer range. Non-destructive testing, including ultrasonic and magnetic particle inspection, is conducted to verify the integrity of the crankshaft. The final stages include corrosion protection, packaging in controlled environments, and preparation for shipment to customers. The crankshaft leaves the production facility ready for installation. Small crankshaft production. The manufacturing of small crankshafts, commonly used in automotive and motorcycle engines, follows a streamlined, high-volume process. The production begins with precision forging, where steel blanks are shaped into crankshafts using automated presses and dies. After forging, the crankshafts are trimmed, cooled, and subjected to CNC machining processes such as turning, milling, and drilling. Advanced automation, including robotic loading systems, ensures consistent high-volume production with minimal human intervention. Heat treatment processes like induction hardening or nitriding are applied to specific areas to enhance durability. Precision grinding follows, ensuring accurate journal dimensions and surface finish to meet stringent quality standards. Once machining and quality checks are completed, the crankshafts are cleaned, coated for corrosion resistance, and packaged for delivery. These crankshafts are produced in large batches and supplied just in time to automotive manufacturers worldwide. To achieve high output rates, flexible production lines equipped with automated measurement and quality control systems are employed. Automated inspection systems, such as laser measurement and coordinate measuring machines, CMM, verify dimensional accuracy. The manufacturing of large crankshafts, often used in heavy-duty engines and marine applications, begins with forging. High-quality steel is heated and pressed using massive forging presses, such as 3,500-ton presses, to achieve the basic shape. The forging process demands significant expertise to ensure proper grain flow and mechanical properties. The manufacturing process begins with precision engineering and carefully planned workflows. Every step, from material sourcing to final assembly, is designed to optimize efficiency and quality. Skilled team members meticulously follow standardized procedures, using advanced tools and technologies to build durable, reliable machines. Throughout production, multiple quality checks are integrated into the process, ensuring that every mini excavator and small dozer adheres to Caterpillar's stringent quality guidelines. The facility employs a collaborative approach where employees are empowered to identify and address challenges, ensuring continuous improvement. Team leads work closely with production staff, providing support and ensuring access to the necessary resources to maintain high standards. Quality control measures, such as pressure tests, electrical system checks, and final inspections, are conducted to verify the machine's readiness for demanding environments. At the heart of the operation is a dedicated workforce committed to excellence. Employees take pride in their craftsmanship, often viewing the machines they build as if they were creating them for personal use. This pride is reflected in the consistent delivery of high-performance products that contribute to the success of Caterpillar's customers worldwide. The Athens facility's emphasis on built-in quality aligns with Caterpillar's legacy of producing dependable, innovative equipment. This approach ensures that every Cat mini excavator and small dozer delivers exceptional value and reliability to its users. The Caterpillar Manufacturing Facility in Athens, Georgia, is a state-of-the-art center for the production of Cat mini excavators and small dozers. This facility exemplifies Caterpillar's commitment to delivering superior quality and performance in every machine. Through rigorous processes and a culture of pride in craftsmanship, the Athens team ensures these machines meet the high standards that Caterpillar customers expect. The CAT 777D rebuild process, carried out by Holt Cat in Texas, exemplifies an approach to restoring heavy equipment to peak performance. Designed to extend the life of off-highway trucks, the process involves replacing over 7,000 Cat parts and performing 350 detailed inspections by skilled technicians. The rebuild begins with a thorough assessment of the machine, which has typically logged around 40,500 hours. Certified technicians dismantle the CAT 777D, ensuring every component is evaluated. Key systems, including the engine, transmission, and hydraulics, are fully rebuilt at specialized facilities to meet stringent Caterpillar standards. This ensures each part operates at like-new levels of reliability and efficiency. The rebuild process requires approximately 1,785 man-hours, reflecting the complexity and precision involved. Using a CAT-certified rebuild approach, Holt-Cat restores the 777D to factory specifications, ensuring performance, durability, and compliance with Caterpillar's latest engineering updates. The result is a machine that performs like new but at 50 to 60% of the cost of purchasing a new truck. The rebuild process not only saves costs but also extends the equipment's life cycle, providing a sustainable and economical alternative to purchasing new machinery. The process begins with vehicle design and engineering, where the body and chassis are structured to accommodate fuel cell stacks, hydrogen storage tanks, and electric motors. The Toyota fuel cell system, adapted from the Mirai fuel cell electric vehicle, is central to the bus's production. Production emphasizes universal design for accessibility, including horizontal seats with automatic storage mechanisms and safety-enhancing features such as high-definition cameras for monitoring surroundings and an acceleration control system for smooth operation. These tanks are integrated into the bus frame along with the AC synchronous motors for propulsion. The vehicle's powertrain system is further supported by a nickel-metal hydride battery, providing energy efficiency and reliability. The production of Toyota's Sora fuel cell buses involves a series of highly specialized processes designed to integrate advanced hydrogen fuel cell technology with efficient, user-friendly, and sustainable transportation solutions. The assembly line incorporates high-pressure hydrogen tanks, ensuring safe storage of hydrogen gas at 70 megapascals, with a combined capacity of 600 liters. It consists of solid polymer electrolyte fuel cell stacks that convert hydrogen into electricity, generating zero emissions during operation. Finally, rigorous testing and quality control ensure that the bus meets safety, environmental, and performance standards. The integration of an external power supply system also positions the bus as an emergency power source during disasters, reflecting its multifunctional utility. The process begins with an underbody wash using high-pressure water jets to remove dirt and debris from the vehicle's underside. As the car progresses, it encounters the top brush, which cleans the roof, while the two wheel brushes target the wheels and lower side panels. Additionally, two small brushes clean intricate areas, and four vertical brushes cover the vehicle's sides to ensure thorough cleaning. A wax arch applies a protective wax coating to enhance shine and provide a water-repellent layer. The lava foam arch then releases a thick layer of foam for deep cleaning and lubrication. Finally, the system includes 4 fixed dryers that remove excess water, leaving the car dry and spotless. The machine features an LED indicator screen to guide operators and users through the process. With an efficient power and water consumption of just 0.1 kWh per wash, the system offers a high return on investment and can wash over 300 cars daily without interruption. The EVA foam brushes used in the tunnel are designed with soft touch technology, ensuring gentle contact with the vehicle's paint while minimizing the risk of damage. These brushes are lightweight and absorb minimal water, reducing pressure on the car's surface. However, proper maintenance and precautions are necessary, especially in extreme weather conditions, to prevent potential damage. Once the base frame components are prepared, they are assembled to form the complete main frame, including the kingpin installation. The production process of custom-made trucks and trailers, specifically 17 units of heavy-duty 2-axle rigid dump semi-trailers, follows a structured sequence to ensure quality and durability. The assembled main frame then undergoes sandblasting to remove any surface impurities and ensure a clean foundation for further processing. The next stage involves the step-by-step production of the trailer body. This phase requires significant attention to detail and precision. Skilled professionals undertake the assembly of the trailer body, including the installation of key components such as the bracket for the movable rear wall. The process begins with the production of the base frame, which consists of 2 heavy steel beams that provide structural integrity. Once painted, the rear hatch is mounted onto the trailer body. The trailers are then equipped with BPW heavy-duty W axles fitted with Trilex rims, ensuring optimal performance and load-bearing capacity. After sandblasting, the frames are primed to protect against corrosion and prepare the surface for painting. Following assembly, the entire structure is subjected to degreasing, priming, and painting to provide a durable and aesthetically pleasing finish. The final assembly stage involves securely connecting the trailer body to the main frame using 136 bolts, ensuring a robust and reliable structure. Following assembly, the trailers undergo thorough inspections to guarantee compliance with quality standards. Once approved, preparations for transport commence. The completed trailers are transported to a German seaport. The trailers are then loaded onto a roll-on, roll-off, RoRo vessel for shipment. RAC Germany relies on Hoig Autoliners, a trusted partner in RoRo transportation, to ensure the safe and efficient delivery of the trailers to their destination. Upon arrival, the trailers are deployed to sugarcane plantations in Africa, where they are utilized for transporting and discharging sugarcane plants on ramps efficiently. Each custom-built truck and trailer is manufactured under the RAC Germany brand. The use of high-quality materials, precision engineering, and experienced craftsmanship ensures that these trailers meet the demanding requirements of their intended applications. The shipping container production industry plays a vital role in global trade, enabling the efficient transport of goods across oceans, railways, and highways. Annually, over 5 million new containers are manufactured worldwide to meet the growing demand for freight transport and storage solutions. China dominates the industry, accounting for nearly 95% of global production, with major manufacturers producing millions of containers each year. The majority of shipping containers are made from Corten steel, valued for its durability and resistance to corrosion. A standard 20-foot container weighs approximately 2.2 tons and can carry a payload of up to 28 tons, while the popular 40-foot container can hold up to 30.4 tons of cargo. Production costs for a 20-foot container range between $2,000 and $3,000, depending on material prices and manufacturing efficiency. Global container production capacity surged as demand for e-commerce and international shipping rose sharply. By 2021, the container fleet had expanded to 46 million TEUs, 20-foot equivalent units, to address supply chain bottlenecks. Despite cyclical fluctuations, the industry is expected to grow at a compound annual growth rate of 5%, driven by rising international trade and the trend toward modular architecture using repurposed containers. Sustainability is also becoming a focal point, with manufacturers exploring recycled steel and eco-friendly coatings to reduce carbon emissions. Shipping containers, already iconic in global commerce, continue to evolve to meet modern logistical and environmental challenges. The production process of GE90 and GEnx composite fan blades at CFAN, a joint venture between GE Aviation and SNECMA in San Marcos, Texas, involves craftsmanship and advanced composite technology. Each blade is handcrafted using over 1,700 pieces of carbon fiber material, precisely cut and layered to achieve optimal strength and aerodynamic efficiency. The process begins with rolls of carbon fiber sheets, which are cut into precise shapes, each as thin as a playing card. These sheets are meticulously laid up by hand to form the desired blade structure. The layering process is crucial in ensuring the strength and flexibility required for high-performance jet engines. Once the layup process is complete, the composite fan blade undergoes a curing phase in an autoclave, where it is subjected to high pressure and temperature to solidify the carbon fiber layers into a robust and lightweight structure. After curing, precision machining is performed to achieve the exact dimensions and aerodynamic profile necessary for optimal performance. Dimensional accuracy is verified through a series of rigorous inspections, including advanced CT scans, ultrasonic testing, and X-ray analysis. These non-destructive testing methods ensure that the blades meet strict quality standards and structural integrity requirements. Following the verification phase, the blades are fitted with titanium leading edges. These titanium reinforcements provide enhanced durability and resistance to impact, extending the service life of the fan blades. Once the titanium edges are securely bonded, the blades are painted and undergo additional quality inspections to guarantee a flawless finish. The entire manufacturing process takes approximately 340 hours per blade, reflecting the high level of precision and attention to detail involved. The completed blades are then shipped to engine assembly facilities, where they are integrated into the GE90 and GEnx engines, powering some of the world's most advanced aircraft. The aircraft engine repair industry is a critical sector within the global aviation market, valued at approximately $50 billion in 2024, with an expected compound annual growth rate of 5 to 6% through 2030. Major players such as GE Aviation, Rolls-Royce, and Pratt & Whitney dominate the market, offering services that include inspection, maintenance, repair, and overhaul (MRO) of commercial and military aircraft engines. On average, modern jet engines require heavy maintenance every 20,000 to 30,000 flight hours, with shop visits costing between $1 million and $5 million per engine, depending on complexity and engine type. The most common repairs involve turbine blade replacement, combustion chamber refurbishment, and fan blade balancing. North America and Europe account for nearly 60% of the global market, with Asia-Pacific experiencing the fastest growth due to expanding airline fleets. The increasing adoption of predictive maintenance technologies, such as AI-driven diagnostics and real-time performance monitoring, is expected to enhance efficiency and reduce downtime. The assembly begins with the preparation of the Trent XWB's distinctive coaxial 3-shaft architecture, featuring a high bypass turbofan design. The engine incorporates a 3-meter titanium fan driven by a 6-stage turbine, an 8-stage intermediate pressure (IP) compressor powered by a 2-stage turbine, and a 6-stage high-pressure (HP) compressor operated by a single-stage turbine. Each module is meticulously assembled, with every component designed to precise tolerances. The assembly of the Trent XWB, the world's most efficient aero engine, is carried out at Rolls-Royce's state-of-the-art facility in Dölitz, Germany. Bringing together over 20,000 precision-engineered components, this process ensures the reliability, efficiency, and performance that the engine is known for. The next stage integrates the annular combustor, equipped with 20 advanced fuel spray nozzles, ensuring optimal combustion efficiency. The dual-channel full-authority digital engine control (FADEC) system is installed to provide precise control of engine parameters and optimize performance under all conditions. Critical components such as the titanium fan blades, reinforced fan casing, and the strengthened core are assembled using technologies developed through the European Environmentally Friendly Engine (EFA) program. These enhancements support the engine's capability to deliver up to 97,000 lbf, 430 kilonewtons, thrust, particularly for the A350-1000, which features a larger and more robust core. Final assembly includes rigorous testing to validate performance, reliability, and fuel efficiency. Every Trent XWB undergoes extensive quality checks to ensure it meets Rolls-Royce's exacting standards. The assembled engine is then prepared for shipment to Airbus, where it will power the A350, providing 25% lower fuel burn and CO2 emissions. The production begins with components sourced from around the world. The forward section, including the cockpit, is manufactured in Wichita, Kansas. Mid-body sections are produced in nearby facilities in South Carolina, while AFT body structures, including the tail cone, are built on site at Boeing's Charleston plant using advanced composite materials. Wings are fabricated in Japan, with additional parts like wingtips coming from South Korea. These components are transported to final assembly plants using the Dreamlifter, a modified Boeing 747-400 capable of carrying large aircraft parts. At Boeing's South Carolina factory, the assembly process is divided into several key stages across an expansive 1.2 million square feet of production space. The mid-body, AFT body, and other sections are joined, starting at position 0 and moving through 8 assembly positions. Advanced robotics and automated systems play a crucial role here. For example, the QuadBot, a system of KUKA robots, drills, seals, and fastens components with precision. Electrical wiring, ducting, and hydraulic systems, spanning approximately 76 miles of cables, are installed during this phase. Interior components, including overhead bins, partitions, and crew rest modules, are produced at Boeing's Interiors Responsibility Center. These elements are tailored to airline specifications, ensuring a unique and comfortable passenger experience. The construction of the British Airways 787-9 Dreamliner is an intricate, highly coordinated process that involves multiple global facilities and state-of-the-art technology. The Dreamliner program employs advanced composite materials, automated systems, and efficient logistics to produce a lightweight, fuel-efficient aircraft with enhanced passenger comfort. The composite structure of the aircraft is built using a resin-infused carbon fiber tow, laid down by automated fiber placement machines. This material is layered and cured in an autoclave to form the durable outer skin of the fuselage. Additional features, such as lightning-resistant electric discharge cloth and smooth surfacer layers for painting, are incorporated into the composite construction. After assembly and systems integration, the aircraft undergoes rigorous testing and painting before delivery. The British Airways 787-9 showcases the precision and collaboration required to create a cutting-edge airliner, merging global expertise and advanced manufacturing techniques. The construction of the Boeing 747-8 Intercontinental follows a highly specialized process to ensure the production of one of the world's largest and most advanced passenger aircraft. Fuselage and structural assembly. The process begins with the assembly of the fuselage sections, which are built at Boeing's facilities in Wichita, Kansas, and transported to the Everett factory in Washington for final assembly. The 747-8's fuselage is stretched by 18.3 feet compared to the 747-400, and its structure integrates lightweight materials and modern aerodynamics for efficiency. Wing design and assembly. The wings, featuring advanced aerodynamics and raked wingtips for reduced drag, are built in sections and include a thicker, deeper airfoil design. Carbon fiber composites are used for the trailing edge and tips, providing strength and weight reduction. Engine installation. The aircraft is powered by 4 General Electric GEnx engines installed beneath the wings. These engines are designed for high efficiency, incorporating Chevron nacelles for noise reduction and optimized fuel consumption. Unlike the 787's GEnx variant, the 747-8's engines are adapted for the wing's geometry and include bleed air systems. Interior and systems integration. Once the primary structure is complete, the cabin interior is installed, including passenger seats, galleys, and entertainment systems. Testing and final delivery. The aircraft undergoes rigorous ground and flight testing to verify performance and safety. Upon completion, it is painted, delivered to customers, and configured to accommodate up to 467 passengers in a 3-class layout. This efficient process makes the 747-8 a benchmark in commercial aviation. The shuttle launch process is a planned sequence of events that ensures the safe and successful liftoff of the spacecraft. The sequence begins well in advance of the scheduled launch time, with various teams conducting inspections, fueling operations, and final crew preparation. Pre-launch preparations. The shuttle is assembled in the Vehicle Assembly Building, VAB, where the orbiter stack, including the external fuel tank and solid rocket boosters, SRBs, is integrated. Once assembled, the shuttle is transported to the launch pad, covering a few miles on a crawler transporter. At the launch pad, pre-launch inspections are conducted to ensure the vehicle's readiness. Crew boarding and final checks. As launch time approaches, the astronaut crew arrives at the pad in the customary Astro van, escorted by a NASA security van. Upon arrival, they pause to observe the shuttle before proceeding to the elevator that takes them to the orbiter access arm. The crew members, assisted by specialized personnel, don their launch and entry suits and begin boarding the shuttle, occupying their designated seats. Following the crew's boarding, the shuttle's hatch is securely closed, marking the commencement of final launch preparations. A critical series of checks follows, including the gimbal check of the main engines. This test ensures the thrust vectoring system is operational, allowing the shuttle to adjust its flight path during ascent. The vent hood, or beanie cap, used to vent gaseous fuel from the external tank, is also removed at this stage. The launch team proceeds through a series of countdown milestones, ensuring all systems are functioning optimally. A significant moment occurs when the access arm is retracted, signifying that the shuttle is almost ready for liftoff. However, the gantry can be quickly returned if any issues arise within the final seconds. Countdown and liftoff. As the countdown nears zero, the ground launch sequencer hands control over to the shuttle's onboard flight computer. At T-10 seconds, the sound suppression water system is activated to reduce the acoustic energy during ignition. The shuttle's three main engines ignite sequentially, followed by the ignition of the solid rocket boosters at T-0, generating over 1 million pounds of thrust each and providing 83% of the total thrust required to reach orbit. The shuttle rapidly ascends, with Houston Mission Control assuming responsibility for flight operations. The shuttle rolls into a heads-down position, aligning itself for optimal aerodynamic performance. The three main engines throttle down momentarily to minimize stress during passage through the area of maximum dynamic pressure, or max-Q. Once this phase is safely traversed, the engines throttle back up to full power. At approximately 2 minutes into flight, the solid rocket boosters complete their burn and are jettisoned, falling into the ocean approximately 150 miles downrange. The orbiter continues its ascent, with its onboard guidance systems adjusting the flight path to maintain the correct trajectory. One critical aspect of this phase is the ice inspection, where NASA volunteers meticulously check for ice buildup on the shuttle. Ice formation can occur due to the supercooled liquid hydrogen and oxygen stored in the rust-colored external tank. Orbital insertion. As the shuttle continues its journey, it reaches speeds exceeding 15,000 miles per hour and an altitude of more than 60 miles. The main engine cutoff, MECO, occurs when the shuttle has achieved sufficient velocity to enter orbit. Following MECO, the orbiter separates from the external tank, which re-enters the atmosphere and disintegrates. A small burn maneuver is performed to adjust the shuttle's orbit precisely. Weather conditions play a crucial role in determining the go, no-go status for launch. A final weather check is conducted, assessing conditions such as cloud cover, wind speed, and atmospheric stability. Once in orbit, the crew begins post-launch operations, including documenting the condition of the external tank and preparing for mission objectives. The shuttle systems are checked for any anomalies, and the mission proceeds according to the planned timeline. The shuttle launch process is a testament to planning, precision engineering, and the dedication of countless personnel working together to achieve space exploration objectives. Each phase is executed with precision to ensure mission success and the safety of the crew. Detailed plans for the Grayhound, based on the original 18th century revenue lugger, were analyzed and refined with structural assessments, stability data, and framing patterns. These plans were provided by Fairley Restorations, who used advanced computer modeling to translate historical designs into actionable templates. The preparation stage resembled assembling a large, intricate jigsaw puzzle, with each component crafted to fit perfectly. This groundwork paved the way for construction to move quickly once the assembly began. A team of 6 full-time shipwrights, including local craftsmen and an apprentice, commenced the assembly. The keel was laid in a celebrated ceremony, marking a significant milestone in the project. Planking began shortly afterward, a labor-intensive phase that required precision and care. The planks were fastened using tree nails, wooden pegs with a history of use in shipbuilding spanning thousands of years. Tree nails offer durability far exceeding that of metal fastenings, contributing to the vessel's longevity. The building process of the Grayhound, a 63-foot replica of a 1776 three-masted lugger, exemplifies the enduring craftsmanship of traditional wooden boat building. Led by experienced boat builder Chris Reese and a dedicated team of local shipwrights, the construction took place at Voyager Boatyard in Millbrook, Cornwall, utilizing historical techniques and modern precision. Throughout the process, the project embraced historical authenticity and community involvement. Over 4,000 sponsors supported the build, with their names and messages inscribed on tree nails throughout the ship, embedding a sense of camaraderie and goodwill into the vessel's very structure. As construction advanced, the ship was equipped with unique features, including 2 early 19th century cannons salvaged from a nearby seabed. These details underscored the dedication to preserving maritime heritage and capturing the spirit of the era. The Grayhound was launched amidst celebration, signaling the culmination of a collective effort and traditional craftsmanship. Though the hull was completed, work continued to outfit and finish the vessel in preparation for her intended use. The production and installation of the lock chain for the IFTA lock involved planning and execution to ensure operational reliability. The need for replacement arose after a critical failure caused by a structural defect in the attachment of the lifting chains to the lock gate. This incident led to the sudden breakage of the chains, necessitating immediate action to restore the lock's functionality. The replacement chains, known as Gauss chains, were manufactured with the highest urgency, achieving a production timeline significantly shorter than the standard duration of 12 to 16 weeks. The chains were produced and assembled using the multi-link plate principle originally conceptualized by Leonardo da Vinci. This design ensures optimal lubrication distribution, enhancing the chain's durability and performance under demanding conditions. Each chain measured 25.51 meters in length and comprised 229 links and 1,832 link plates. The chains were engineered to meet stringent requirements, including a minimum tensile strength of 1,200 newtons per square millimeter and a calculated braking force of 2,200 kilonewtons. A total of 4 chains were fabricated for the project. Once delivered, the chains were installed with precision at the IFTA lock. This swift and efficient response was critical in minimizing downtime and ensuring the continued operation of the lock system. The explosion-proof firefighting and reconnaissance robot is a state-of-the-art solution for handling fire emergencies in hazardous environments, such as chemical plants, oil refineries, and areas prone to explosions. Built on a robust tracked robot platform, it ensures excellent mobility on uneven terrains, rubble, and slippery surfaces. The robot features a powerful water cannon or foam dispenser that can extinguish fires effectively from a safe distance. Its high-pressure system can deliver a large volume of extinguishing agents, even in challenging scenarios where human firefighters cannot safely operate. Remote control and wireless communication technology ensure the robot can be maneuvered from a secure location, protecting personnel from exposure to flames, toxic gases, or collapsing structures. The robot's explosion-proof design includes flame-resistant and sealed materials, preventing the ignition of flammable gases or vapors in high-risk areas. It is equipped with advanced sensors like infrared cameras, gas detectors, and thermal imaging systems, enabling real-time monitoring and reconnaissance in extreme conditions. This capability allows operators to assess the fire situation, identify potential hazards, and determine the safest approach remotely. Additionally, its track platform provides superior stability and traction, enabling it to navigate obstacles and operate in confined spaces. Some models also include autonomous navigation capabilities, using artificial intelligence to optimize movement and firefighting efficiency. This innovative robot not only enhances firefighting effectiveness but also minimizes risks to human life, making it a critical tool for modern industrial safety and emergency response.